Today we're learning about dilations. Dilations are the only non-rigid transformation that we learn about in 8th grade. So they don't stay the same size. They actually get bigger or smaller. That's why they're called dilations. And one way to think about dilations is that all the points of the shape change distance from one point, and that one point is called the center of dilation. And how you tell how far they change their distance is by something called a scale factor. Now, all dilations kind of use this equation. You start off with your original distance from the center of dilation. Then you multiply that by the scale factor. And usually the scale factor is given to you. They might say the scale factor is 3, the scale factor is 1/2. It can be a lot of different numbers. And then you get what the image's distance is from that center of dilation. If you were to look at your points on your shape, they're obviously not going to say original, they're actually going to have letters. So another way we could write this is that if we have a point A, its distance from the center, or C, is represented by AC. Really easy. So the not primes, I'm going to call our scale factor F, but it's usually just one number. So AC times F equals the primes. So our not primes times our scale factor equals our primes distance from the center of dilation. Let's go ahead and apply this in some examples where we do dilations. So I have my points here in the triangle JKL, and in order to dilate this triangle, I'm going to go straight from each vertex of the triangle. So I have J, and it says dilate from the origin with a scale factor of 1/2. See, that scale factor was given to us. And I could find the distance of J by using the Pythagorean theorem. I'm actually going to do it an easier way. J is at the point 2, 8. So I know that J originally goes 2 this way and then 8 this way. So I'm just going to have my distance by having both of the directions that it goes, and that will have the whole thing. So here I have 2. I could either do this in my head and say, what is half as far as 2? Well, that's easy, that's 1. But sometimes you can't do it in your head very well, so I'm actually going to write the equation for you. It was the original distance times the scale factor, which was given to us, of 1/2. And then that way we can find the original distance. And that are, not the original distance, the image's distance. And 2 times 1/2, if you were to figure that out, it equals 1. So you could either do that in your head or do the equation. So we will go 1 in this direction. Then we need to find half as far as 8. And you can probably do that in your head too, but I'm going to show how you would calculate that. It'll be 8, the original, times the scale factor, which was 1/2. And you can find that that is 4. So I'm originally went 8 up. I'm going to go 4 up now. And my new point, J prime, will be right there. Now I'm going to do the same thing with L and K, but a little faster. One thing I notice is that if it's from the origin, the distance is actually represented by the coordinates. So you could technically do this with the coordinates if you're doing it from the origin. Frequently, you don't do it from the origin, so you actually have to count it out though. So let's see, L is at the point 6'2". So I want half as far as that. So 1/2 times 6 will be 3. And 1/2 times 2 will be 1, or half as much of 2 is 1. So I'm going to go to the point 3, 1, and that's my new L prime. And then K is at the point 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. So we're going to get half as big as 8, and that's 4, and half as big as 6, which is 3. So my new K prime will be at 1, 2, 3, 4, 1, 2, 3, right there. So I'm going to erase my lines that I drew here and just graph my triangle. Now, something that we should take in mind is that there are some things that we notice with this equation. This equation holds true for not only the distance from the center of dilation, but it also holds true for the sides. So I'm going to write that down. This is our distance from the center. And it holds true for the side lengths. If you were to look at our original triangle, you'll notice that this JL went 1, 2, 3, 4, 5, 6, and then this one went 4, and then this one goes 3, and then 2. So actually all the distances of that triangle were changed by the scale factor, which is really nice. So if you were given the original length, you could find the new length by just multiplying it. The things that do not hold by this equation are things like the area. So when we multiply all the side lengths by a number, the area actually changes by that number squared. So it's actually going to be changing by the scale factor squared. And then another thing is that the angles don't actually change. The angles stay the same, so that means that our new shape will be similar. In other words, it's the same shape, but it has a different size. That's usually how I think of similar. So you can use those things, like if you were just given the side lengths and the scale factor, you could figure out the original, or you could figure out the image. So let's say you're given that the image is side length, let's say AC prime, that its side length is 2. And then you're given that your scale factor is 4. Now you can find what the original side length was by just figuring out what would go in this blank. So what times 4 equals 2? You can find that by dividing 2 by 4, and you'd get that the original side length was 1/2. So this is actually really useful. You don't have to necessarily draw it all the time. You could just use this little equation right here to help you out.